Okay. All right, so we are going to talk about independent and dependent events and then like multiple events happening. All right, so how this affects our probability. So one of my little mnemonics is, well, not really a mnemonic, but the way I think about it is that if it's a multiple events, multiple picks, I multiply the probabilities. Okay? Now, what makes a difference on what probabilities I'm multiplying together is dependent upon if it's an independent event or if it's a dependent event. So if you notice that if it's independent, we have that this formula holds true where the probability of A and B happening is the probability of A times the probability of B. Okay. If it's a dependent event, meaning, we'll talk about that in a second, then it's it's the probability of A happening times the probability B happens given that A has already happened. Okay. So let's talk about, what does this mean? Independent versus dependent. So independent events are events in which one outcome does not affect another outcome. So in which one outcome has no effect, right, on the second outcome. For example, picking a card and flipping a coin. Right? Whatever card I pick is not going to influence whichever card I pick is not going to influence me flipping the coin. Again, don't try and read into too much of these. If it's independent, it will make life a lot easier to just try to not think of a loophole. Okay, if it's dependent, that's going to be an event which, the first event's outcome is going to affect the second event. Outcome affects the second outcome. So, for example, what I always say is if you are picking a marble out of a bag or a name or out of a hat or whatever, if I put the name back in, then everything's fair for the next pick. If I hold the name out or if I hold the marble out, then all of a sudden things are changed. So when we see things like without replacement, that should be like your little red flag. The light bulb flicks on, ooh, that's going to change things for the next person that goes. So if we're picking cards and the goal is to get the ace, right? There's only 4 of them in the deck. If you go ahead of me and you pick a card and it happens to be an ace, and you hold on to it, meaning you didn't put it back in the deck. Now I only have 3 chances to win out of the 51 cards. Okay, so things would change. My probability changes from the first outcome to the second outcome. Okay, and so that's where we look at, what's the probability of the first outcome, probability of A, and then what's the probability of the second thing happening given that the first thing has already happened. Okay, so let's take a look at just kind of some examples. We can talk about if they're independent or dependent, and then we can kind of go through how do we solve the probability. Okay, so I flip a coin and I roll a 6-sided die. Okay. If I flip the coin, whatever I get, heads or tails, is not going to affect the outcome of rolling that die. So this would be an independent event. Walker, you got to quiet down, bud. So what we're going to do is let's find the probability that we flip a head and then we roll a 5. Okay, so probability of getting heads and then roll a 5. Okay, so I'm putting a comma in between these. Sometimes we might see like heads, then 5, whatever, but this kind of lets you know there's 2 things first happening. So since this is independent, we want to know what's the probability of these both happening. So it's the probability of getting a heads times the probability of rolling a 5. Okay, so getting heads on a flipping a coin, that's a 1 in 2 chance. The probability of rolling a 5 is a 1 in 6. Unlike before with the addition rule, multiplication, it doesn't matter what the numerators and denominators are. So I can just multiply numerator to numerator. It's 1, denominator to denominator, and that's 12. So I have a 1 in 12 chance of flipping the coin and it landing on heads and then rolling a 5. Okay. Let's look at another one. There's 10 beads, 2 black, 3 white, 5 red. Make sure that all adds up. Yep. 2 beads are selected at random. Find the probability that you first pull out a red bead and then you pull out a white bead without replacement. And that is key right here, without replacement. One of the things that I tell students is to, sometimes it can be confusing because we think of this happening like they're grabbing both of them at the same time. If it's easier, like for me, I think of it as happening, one is happening right after, right? So when I first do this, right, we're looking at probably the probability of pulling out a red and then going to be a white, okay? So it's 2 things. We're doing multiple picks. We're picking out 2 times. So multiple picks, we're going to multiply that probability. So now let's talk about this. Without replacement, that means it's dependent. Okay, so this, the probability of it being a red, the first time that we pick this, that's pretty easy. There's 10 of the beads and 5 of them are going to be red. So we have a 5 in 10 chance. Now we are multiplying, but remember we didn't put the bead back in. So now we have to look at what's the probability of picking the white, given that someone has picked the red bead and has taken it out already. Okay, so this is kind of how I'm writing it, but in context like this, it's a little bit different than we were looking at the table. So we're picking a white one, given that one of our red ones is already been picked and taken out. So now of the white beads, there's 3 white beads, but we know that there's only 9 of them because one of our red ones was taken out. So pick white, given a red one was already picked. If I go ahead and multiply this out, this is going to reduce. This is really 1/2 times 1/3, which is 1/6, but 15 over 90, which is going to be 1/6. Okay. So sometimes when we're thinking of this in terms of the context, you can kind of think what's going to happen next. That's a little bit easier. When we do some of these other problems, sometimes it's a little bit harder for us to think about that. If the Atlanta Hawks free throw percentage is 82%, right? Meaning 82% of their shots go in. What's the probability that a player for the Hawks will make 2 free throw shots in a row? Okay. I guess we're missing the word throw here. So I'm going to use, 0.82 because 82%, like times 82% is going to be kind of goofy. So let's use a percentage, which I probably prefer to use as a decimal anyway. So 0.82, that's the first shot, right? It doesn't change. We're just kind of using this. They've been doing these statistics over a long period of time. So, making one more basket isn't going to dramatically change the free throw percentage. So we're going to call these independent, right? Some could argue that it's dependent, but we're going to just say that, it's kind of a long-term stats. They do a lot of the free throw shots. So we're not going to say dramatically that it affects one other. Or if you think about it as far as one player making it and then the second player doing a free throw type of thing. Okay, so if we're looking at that, we're going to multiple shots. We're going to multiply the probabilities. This is independent. We're not, one is not, if I make the first one, it doesn't mean that I'm automatically going to make the second one. Okay, so I multiply these probabilities together, and this is why I used a decimal, because if I did 82 times 82, I'd get a ridiculously large number. Here I get 0.6724. So that roughly is 67.2% chance that our Hawk player is going to be making this 2 times in a row. All right, let's look at another example. And this is a little bit different. So we're going to kind of go back and we're going to look, what's the probability that a person has been to Mexico and been to Canada? Okay, so I'm looking off a table. So really this is like probability of Mexico, the intersection with Canada. Okay, M for Mexico, C for Canada. This is not a given situation. We didn't say anything. We just said, they've been to both places. So we are looking for the intersection of Mexico and Canada. And that's 6 people out of 25. Okay, 6 out of 25. This is an is an intersection. So we look to see where do they intersect out of the total amount. Okay, now it asks, what's the probability that a person has been to just Mexico? So we look Mexico, there's been 9 people out of the 25 people surveyed. And then what is the probability that a person has been to Canada? And to Canada right here, 11 out of the 25. Okay, now they ask, are these have been to Mexico and have been to Canada, are they independent or dependent? How the heck can we tell? Well, remember this formula right here, that's up here, that says probability of A and B, that intersection, both things happening at the same time, is if it's independent, it will be equal, those products of those probabilities would equal that intersection. So we can check this. We know that this was the probability of Mexico. This was the probability of going to Canada. And so we're really going to see, does the probability of this intersection equal the probability of Mexico times the product, right? Times Canada. Okay. If so, it's independent. So let's check. We're going to say, so we're going to ask, does this equal, right? Mexico is 9 over 25 times 11 over 25. Well, I'm going to have to bust out the calculator here. We get 99 divided by 25 squared, because remember, it's tops times top over bottom times bottom. And that ends up being 0.1584. Well, let's see what that looks like if I turn that into a fraction. Okay, it's 99 over 625. Okay, clearly this is not independent here because they don't equal each other. So all right, so if it were independent, then those two, the product of these two probabilities would equal that intersection. Okay, so 99 over 625. I said 6 divided by 25, that's, 0.24. So this looks like crazy, like, oh, no way. But I mean, really when we compare the decimals, they're not way out there, but they're not the same. So if it's not independent, so this would be dependent then. So there is some sort of relationship between that travel. Okay, let's look at a couple other examples here on the back. So in a certain town, we've got the probability a person plays sports is 65%. And the probability that a person is between the ages of 12 and 18 is 40%. So we've got this and a person playing sports. And then the probability that a person plays sports and is between those ages, so both of them, is going to be 26%. Yeah. So I'm going to let this be A and this be B, right? And we'll say this is A and B, right? Because that's A and B. So remember, if our probability, if it's independent or not, if it is independent, then we can see if it's independent, then the probability of A times the probability of B would equal the same as the probability of A and B. Okay, and this is statistically speaking. So again, I'd encourage you in a percent situation, let's change this into a decimal. So the probability of A is 0.65. The probability of B is 0.4. So if I multiply these together, I get 0.26. And look what happens right here. This equals 0.26. Therefore, these are independent. I-N-D-E-P-E-N-D-E-N-T. There we go. So um, 0.26. And yes, this checks. All right, let's take a look at this one. And this is kind of what you might see some of your tables looking like. Notice it's not quite as nice as some of the ones we've been using because we always had room for the totals on here. So our tables are a little bit different. Let's take a look at this. So we have the survey, and usually, you know, if you take the survey, you might just be recording the information. You might not total it all. So this table shows the data that they collected. We're going to look at, does having a job and being 18 or greater, are they independent or dependent? So let's take a look. So, and job. So probability of having a job and then probability of being 18. So we really need to check, does the probability of having a job times the probability of being 18 equal the probability of doing both, which is the job and 18. Okay, so probability of having a job, well, we got to think about this. The probability of having a job, there's a lot of people that's 607. And I'm going to just kind of do my totals over here. 245 plus 92, that's 337 that don't have a job. And if I add these together, I should get, all right, 944. And if I do the same thing down here, less than 18 or greater than 18, right, 587 plus 92, that's 679. And this is 265. Just to double check. Yes, it does work, right? Every once in a while there's a math mistake, but this one works. So it works both ways. The totals work both ways. So we've surveyed 944 people. So the probability of finding someone that has a job in our survey, well, of the job, that was 607 out of 944. Holy cow, that's a lot. All right. I might have to turn these into some decimals. Okay. And if I'm looking at this one, probability of them being 18 or greater, right? So that's 18 or greater, that's 679 out of 944. All right, let's see what that is. The calculator is definitely coming in handy. Remember, it's top to top over bottom to bottom. So 607 times 679. Right, that's a huge number, divided by, oops, I don't need that comma on there, 944 squared, because 944 times 944. And that ends up being 0.46, I'm going to write them all out, 0.4625. All right, well, there's this one. Let's find the probability of the intersection. They both have a job and are over 18. Notice we're still talking about the whole group. So this is the intersection, has a job and 18 or over. So that's 587 out of 944. Let's check and see 587 divided by 944. And this is 0.6218. So since these are not equal, right? Those are not equal. So this would be dependent events. Which kind of makes sense. Most people are going to get a job after they become 18. Right. So as we look at this, these are dependent, and that's how we can statistically show this. All right. Another one, and kind of bring it back here full circle. Probability of getting accepted into Harvard, not great, 5.4%. Probability of getting accepted into Stanford, even less, 4.8%. So assuming these events are independent, meaning that like you're getting, it's not going to affect your admissions, getting in one or the other. So what's the probability that Karen will get into Harvard or Stanford? Okay. Before we start thinking about multiplying or anything of that nature, remember, what does that mean, or? Harvard or Stanford. Okay. That, even though they are independent, that might mean that they are mutually exclusive. We don't multiply in an or statement, we add them. So probability of getting into Harvard times the probability of getting into Stanford. Since it's independent, we're going to think of that as a mutually exclusive. There's not an overlap. So in this case, because it's independent, we're going to be subtracting off that 0. Okay, so one's not having an effect on the other. So as I look at this, oh, I put multiplication. We need to add them. I think I said add, and I still put multiplication. So 5.4%. I'm just going to still write this as that, moving that. So in the other one, 0.048. And if I add these together, right, 0.054 plus 0.048, we end up with 0.102. And so the probability of getting into Harvard or Stanford would be, and then multiply it by 100 if you're not sure, it's 10.2%. Okay. If it said what was the probability of getting into Harvard and Stanford, then we would be looking at multiplying the two together, right? So that's the difference between the addition rule, it's an or, and the multiplication rule would be an and for independent events. Now, here's a good one. What's the probability that Karen doesn't get into either of them? So here's what the probability was that she got into one or the other, right? So if it's not like she doesn't get accepted into either of them, would be like, no Harvard, no. So really, it's the probability of Harvard or Stanford, but not happening, which is really just 1 minus the probability that it does happen. Okay, so remember how this was 0.102? So let's see, 1 minus 0.102. So if there's just over a 10% chance that she gets into one or the other, there's pretty much almost a 89.8% chance, right? 89.8% chance that she doesn't get into either of them. Okay, so this is the possibility she gets into at least one, right? One or the other. This is the probability, that she doesn't get into either of them. It's the other part. It's the complement. You either get into one or the other, or you don't get into, you don't get into either of them. Right? And if I wanted to find the probability of getting into both of them, then I would multiply those together. All right. So let's see, this last example, what's the probability of selecting 2 5s in a row from a standard deck of cards? Okay, this is dependent. Okay, and this is one that I think sometimes might be a little bit easier to think about the probability of getting a 5 on the first pick, right? First pick. And then we're going to be multiply getting a 5 given a 5 is been, oh, it doesn't say two 5s in a row. All right, so we're going to do this 2 ways. Doesn't necessarily say. In the first one, I automatically was thinking that we're keeping one of the cards, but it doesn't specifically say. And most times it would need to, because you'll see the difference. So on our first pick of getting a 5, there's 4 5s in the deck of cards that has 52 cards, right? This would be without replacement. Okay. If I hold on to that first 5, the next person that goes to pick a card would be, there's only 3 5s left, so you only have 3 chances to get that 5, and there's only 51 cards. Okay, so if I look at doing this, this would be 12 over 52 times 51, which is a big number, 26,552. I'm going to go ahead and just turn this into a percent, because that might mean a little bit more to us, right? So 0.004, if I multiply that times 100, I basically have a 0.45, 45%, right? 0.45% chance of picking that. Those odds are not great, right? Picking the cards, 2 5s in a row. Let's see, how does that change if it were independent, right? Meaning with replacement. So we pick the card, then we put it back in, shuffle, and then you pick it again. Okay. All right. So the probability of getting a 5 on the first one, and that first pick is 4 out of 52. Since this would be independent, we put it back in, the probability of getting a 5 a second time hasn't changed because the cards are all back in there. There's still 4 out of 52. So if I multiply those, now I've got 16 out of a still large number. 52 squared is 2,000, even bigger. Okay, and let's compare this, because to me these fractions are hard to even tell. So let's see what this looks like as a percent. If I do 16 divided by that answer, okay, and if I want to multiply it by 100, so take a look at what does that look like. It's still pretty slim pickings, but it's 0.59%. So slightly better chance of getting 2 5s in a row, with there being, even though there's, you know, one more card here, but there's one more chance for it to win. So as we're looking at these, you know, you have a lot of times with the independent and dependent events, remember, if it's multiple things happening, we're going to multiply those probabilities. If it's dependent, it's just multiply the one probability by the other one. I'm sorry, if it's independent, multiply with the 1 times the second one. If it's dependent, we have to think what's going to happen to that second probability. Usually there's a kind of a change in there. So make sure you're practicing, and, you know, we've kind of covered a lot of these symbols. It is like its own little language. And the best way to get familiar with it is by practice and just exposing yourself to as many possible situations that you can see until it really starts to feel comfortable with it.